In this unit, we'll be learning about the chemistry of living things. It's going to be very basic kind of organic chemistry and biochemistry. And when we're studying chemistry, we're studying essentially matter. And matter, if you want to write another word in, essentially matter is stuff. That's a fancy science word, right? Stuff. It's the stuff that the universe is made of, at least the stuff that we're familiar with, like stars and planets and human beings, other animals, the desk, water, plants, everything that we're familiar with is made of matter. And matter is this stuff that has two properties, intrinsic properties, mass and volume. Mass essentially means that it interacts with gravity and it has a certain amount of stuff, the amount of atoms, okay? So like I, being a larger person than you, I'm more massive than you are. Volume then is how much space that matter occupies. So I'm a larger person than you, so I also occupy more volume than you do. If I had a baseball, I could hold it in my hand, I could measure and see how much space it occupies, that'd be its volume, I could see how heavy it is, that would give me an indication of its mass, how many grams and so forth. It gives me an indication of how much stuff is in it. Matter exists in three different states, solid, liquid, and gas. That won't be on your exam, but you should know that. That should be pretty basic. There actually is a fourth state of fourth state of matter that you might remember, and that actually is plasma. And a plasma is really just an ionized gas. A flame would be a good example of a plasma. The ball of fire that we call our sun would be an example of plasma, and so forth. Water is a very special molecule. We'll talk about it at the end of this lecture, and the beginning of the entire next lecture will be about water and its special properties. Water is actually critically important for life, and one of the cool things about water is it's the only thing that exists in all three states in nature. There's solid ice at the poles. Of course, there's tons of liquid water on the planet, and there's lots of atmospheric water, the water vapor in the atmosphere. Water is critically important, like I said, for living things. There's a reason why your body is made of cells, and those cells are essentially bags of water with stuff dissolved in it. There's a reason why we wash ourselves and wash our dishes and our cars and whatnot with water. Water's got some really cool properties. We'll look at it at the very end of this lecture, like I said, and the next lecture will be all about water's special properties. You have these notes on page 1, and atoms are the building blocks of matter. So we now know that the stuff, this matter in the universe is built from atoms. Atoms look, we believe, like this. In the nucleus of the atom, you have the protons and the neutrons. They have a positive charge and a neutral charge. Think pro. Think, like if I'm pro something, I'm positive in that direction, right? Neutron comes from the word neutral, which means if I'm neutral on something, I'm not really for it or against it. I'm kind of in between. I'm nothing. Neutral means no charge. So the positive protons and the neutral or no charge neutrons are in the nucleus. And then orbiting around the nucleus are the electrons, and they have a negative charge. Now, interestingly, protons and neutrons have about the same amount of mass. This won't be on your exam, by the way, just kind of a little fun fact here. Protons and neutrons have essentially the same mass, but electrons are absolutely tiny by comparison. Electrons have 1/1840th the mass of a proton or a neutron, so they're absolutely tiny. In fact, they're so small that when we're considering the weight, or a better word would be the mass of an atom, we're calculating that. We don't even consider the electrons. Even if an atom might have hundreds of these electrons, we don't care, we don't consider them. So that's what these notes say. The nucleus is in the center of the atom, and it's where the protons and the neutrons are, the positively charged parts of the atom and the neutral parts. And the electrons orbit around the nucleus, and sometimes they're called shells, sometimes they're called clouds, sometimes they're called orbitals. You'll get into more detail with that next year in chemistry. Then we have the elements, and there's that periodic table of the elements. Elements essentially are kind of interchangeable with the word atom. Imagine if we had all of one particular kind of atom, we could then say, okay, this is the element oxygen. This is the element helium, hydrogen, carbon, calcium, whatever it might be. Now you have your periodic table of the element, and in each box, there's a box like this for each element, or each atom, and it has the same information pretty much on all the periodic tables you'll see. The first thing it'll say is it'll say the name of the element, like helium, and they'll have the symbol, which is He. So maybe you'll remember some other ones, calcium would be Ca, Lithium is Li, potassium's kind of funky when it's K, iron is Fe, and so forth. Okay, so it'll have the name, and then it'll have what's its symbol. Then it has the atomic number and the atomic mass. Okay, the atomic number, in this case 2 for helium, it tells us the number of protons, and it also tells us, there's something else you need to know, it also tells us the number of electrons. It tells us the number of electrons. So helium has 2 protons and 2 electrons. Now if I think about that for a minute, hang on, if I think about that, if it has 2 protons, what are the charge of a proton? Well, they're plus, so I have 2 plus. And if I have 2 electrons, the electrons are negatively charged, so I have 2 negatives. So what's my overall charge for a helium atom? Well, it's 0. It's neutral. All elements in their elemental form have no charge because they have the same number of protons and electrons, and that is laid out with the atomic number. All right, so I know 2 of the 3 things I need to know to draw this atom. If I was asked to draw helium, I need to know how many protons, how many neutrons, how many electrons. I already know protons and electrons, so I just need to know neutrons for neutrons. Now we're going to look at the atomic mass number. This is where this comes into play. Remember, when you hear the word mass, think essentially like weight, okay, at least for our purposes. So the atomic mass tells us how much does this atom weigh. If I could put it on a scale, what would it weigh? And so if we think about it, remember, electrons are so small we don't even consider them. So really what this number reflects is what is the number of protons and neutrons in the nucleus of the atom. In this case, it's 4. So I know that total protons and neutrons is 4. All right. Now I also know that I have 2 protons, so I can just subtract and solve the fact that I must have 2 neutrons as well. This should not be too difficult for you. Imagine if I gave you another atom. For example, fluorine. Fluorine, right here, is the F. It has an atomic number of 9, an atomic mass of 19. What that tells me is that my total number of protons and neutrons is 19. And it also tells me that 9 of those are protons, right? Because that's what this number means. Right? This tells me the number of protons and electrons. So how many neutrons must I have? Well, I must have 10 neutrons. So it should not be difficult. You should easily be able to draw any element that I give you if I just give you this box of information. There are a number of elements that are important for living things. For example, if I were to bust your body apart into all the different atoms, we'd find a lot of calcium because there's lots of calcium in your bone. We'd find a lot of iron because there's iron in your blood. But the ones that we'd find the most of, actually, the most important elements for all living things, not just you, but all living things, are these ones. And there's actually a specific way that I'd like you to write them, a specific order. So please write them in this order on your study guide. First we have the C, which stands for carbon. If you don't remember that, write it down. Then we have hydrogen, which is the H. Then I'd like you to write N, which is nitrogen. Then the O, which is oxygen. The P, which is kind of a weird one. You might think potassium, but no, potassium's a K, remember? P is actually phosphorus. And then lastly, I'd like the S for sulfur. So go ahead and say that word with me, chnops. Chnops, you need to memorize that. The most important elements for living things is chnops. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Now, why did I give you that funky word chnops? Well, one is I think that it's a pretty easy way for you to memorize it, kind of a funky word to just memorize chnops. But the other thing that's nice about it is it has the C first. And remember, the C stands for carbon. Carbon is the most important, it's not even close, most important element for living things. Somewhere over, maybe kind of on this side or somewhere over here, write in that life on planet Earth is referred to as carbon-based. Carbon-based life. All life on this planet, whether it's you, bacteria, or a plant, is based on carbon. What does that mean? Well, what we're going to see later is that the molecules that are used to build cells, things like, for example, fats, essentially look like this. And we draw them like this in organic chemistry, and we don't even include that these are all carbons. All these little points here are carbons. You'll find other molecules look more like kind of rings like that, or pentagons. And again, these are all carbons here, for the most part. Carbon is a pretty cool atom because it has 4 valence electrons. And because it has 4 valence electrons, it can easily make 4 bonds with other atoms. And so as a result, carbon makes a great backbone molecule. These are all carbons, and then coming off of them can be hydrogens and nitrogens and oxygens and so forth. Same here. So because carbon has this cool ability to form 4 separate bonds with 4 other atoms, it makes a great molecule for building, makes a great atom for building really complex molecules. So as a result, the kinds of molecules that are used to build life are carbon-based, and as a result, life on planet Earth is carbon-based. Physical properties and chemical properties. So a physical property, think of it like, stuff that you can observe directly. How does it look? What color is it? How hard is it? Will it cut a diamond, or will a diamond cut through it? What does it smell like? Does it have a taste? What's its boiling point? What's its melting temperature? Now, physical change is where we change what state it's physically in, but we don't actually change what it is elementally. So, for example, solid water. You may remember, I hope, that water is H2O, 2 hydrogen atoms and an oxygen atom, pretty small molecule. Well, when it's solid water, it's H2O, ice. Then if I melt it, well, now it's just liquid water, H2O. And if I even boil it, now it's water vapor in the atmosphere, it's steam, right? It's still just H2O. I've just changed what state it's in, but I haven't actually changed what it is as far as the elements. Now, chemical properties, on the other hand, now we're actually interested in what are the elements in it. What are the atoms that it's made of? Classic example here. This picture showing us what? What is this? Well, people say this is rust. Okay, it's rust. Rust is iron oxide. What happens is we have this iron can, which is Fe, and usually in the presence of water and our oxygen atmosphere, it rusts and it forms a new compound called iron oxide. Iron, the iron atom, and oxygen. And we get this iron oxide. Notice it has very different physical properties from the iron can. It's not as smooth, right? It's more rough looking. It's a different color. And it's because it's a different thing. Physical change would be like this example, right? Ice melting into water, water boiling. It's still water. We haven't actually changed what it is chemically. Chemical changes. Here's a classic one. You pour 2 clear liquids into each other, you get this new yellow thing, this yellow solid. A combustion reaction is another great one. Now, I'm going to give you some examples. I want you to write this at the very top of your study, way at the top. I want you to write, and these are signs that you're seeing a chemical change. So here we go. Color change. If you see color change, you're thinking chemical reactions happening. If you see light being produced, like in this fire here, light's being produced, chemical reaction. If you see temperature change, that's another one. If it gets hot or if it gets cold, obviously this fire is getting cold. Maybe you've had one of those ice packs that when you break it, all of a sudden it gets cold. What you actually have there is 2 different chemicals separated by a plastic or maybe rubber divider. When you break it, they mix, it gets cold. So temperature change is another one. If a gas is produced, this fire is producing a gas, CO2. We'll get back to that in a second. And then the last one is if a solid is produced. So in this example, you have 2 clear liquids poured together and you get this yellow solid. It's a classic example you'll see in a chemistry class. So with a fire, what you have, imagine like if I have a candle and I light it. Yeah? So I've got a candle and then I light it. All right. What's actually burning is wax. Yeah, you probably are familiar with this. Now wax, if I actually looked at what it is, it's essentially fats. And fats, like I said before, essentially look like this. And what's actually happening, remember these are all carbons, right? What does that fire need to burn besides the wax? Well, it needs oxygen, yeah? The oxygen goes in. And what ends up happening essentially is that these bonds right here are broken. And what gets released, this individual carbon gets released in the presence of oxygen to form what? CO2, among other things. There's other gases being released here as well, but one of the big ones is CO2. This happens when you burn any what's called a hydrocarbon, whether it's waxes or the carbohydrates that are in this log, or whether it's a petroleum product like gasoline, octane, whatever it might be. Now, little side note, does my body do something similar? Does my body and your body, do we take in fats and carbohydrates, and then do we burn them in the presence of oxygen? Do we give off heat and CO2 like this fire? Absolutely. If I take away this oxygen from this flame, fire will go out. If I take away oxygen from me, I'll die. So there are very interesting analogies to be drawn between these two processes, and we'll see that in a couple of chapters when we're in the cellular respiration unit. Compounds. So now what we're doing, remember we started with electrons, protons, neutrons, making atoms. Now we're going to take multiple atoms and stick them together to make compounds. Here's a classic example. Sodium chloride. Sodium chloride is a compound made from sodium and chlorine. So sodium is an interesting one. Sodium, you can't buy this in stores. It's actually a really, really nasty atom. It's a solid at room temperature, and it's so reactive that if you put this thing in water, it will actually explode. So very nasty atom, very reactive. Certainly wouldn't want to eat it. Then we have chlorine. Chlorine is a gas at room temperature, and you'll see that it's a yellow color. Maybe you'd call it a mustard color. It's a mustard-colored gas, hence mustard gas. This is a very poisonous gas. It was one of the components in mustard gas that was used to kill people in World War I. So definitely nothing you want to be exposed to. But what's interesting is if I were to take a little bit of this sodium that explodes in water, and I were to drop it into this poisonous gas, what would happen automatically is that I would start to see a white crystalline solid start to form, and this white crystalline solid would be sodium chloride, these two atoms put together, and that is, of course, table salt, which I can not only eat, but actually is a necessary part of my diet. So, make a note somewhere on your study guide that the compound, its properties are unique and oftentimes very different from the elements that it's made from. So these two things are very nasty, put them together, and they're totally fine. Little side note here, this is something you should keep in the back of your mind. Sometimes in our society you'll hear people say something like, oh, you definitely shouldn't be taking whatever it is. Because it has this particular element in it. Let's say mercury, maybe, for example. And so, oh, you shouldn't do this, or you shouldn't expose yourself to that because it's got this particular element in it. Well, understand, it may actually be dangerous to you, but there's also a possibility that that particular element, though in an elemental form it's dangerous to you, like sodium and chlorine, taken together in this particular product that you're choosing to take may not be dangerous. So, just kind of leave it at that for now. We'll talk about that in a little more detail later, but just understand that kind of in the back of your mind that oftentimes these compounds behave very differently than the elements they're made from. Ionic bonds. Ionic bonds are the bonds formed when one atom loses its electron and transfers it to another. So, in the case of sodium and chlorine, why do they come together? Well, it turns out that sodium has one extra electron in its outer orbital. All of the atoms on the planet want to be like the periodic table elements that are far over to the right, the ones that are called the noble gases, starting with hydrogen or helium and working your way down. Those ones are noble gases because their outer orbitals are totally full. Sodium's unhappy because it has one extra. It has a full orbital and then it has this one extra electron hanging by itself that it'd love to get rid of. Chlorine would love to get one more electron so its outer orbital can be full and it can behave like a noble gas. So what happens when we put them together? The sodium loses its electron and gives it to chlorine. This picture does a really good job of showing it. So this is your classic ionic bond. Sodium, like I said before, its outer orbital is full except for it's got this extra electron in its furthest most outer orbital. So it has what we say 1 valence electron. It'd love to have 8 in its outer shell. Chlorine has 7 valence electrons. It needs one more. So it's a match made in heaven. You bring them together, sodium loses that electron, chlorine picks it up. Now they both behave very happily, like our noble gases. They both have their outer orbitals full, and as a result, they also behave very differently. These two are both very reactive and very nasty, but now they're not because they're happy. Little side note, notice that their charges change. They go from being neutral to being positive, or neutral and being negative. Why is that? Well, sodium, what's it doing? It's losing an electron. What's the charge of the electron? Negative. So as that negative leaves, it then becomes positive. The chlorine, as it takes on that negative charge, now becomes negative. This is how it works with ionic bonding. These now are called ions. So an ion is this charged now element that has a charge to it. It's not neutral anymore. Molecules are similar to compounds, but they, instead of ionic bonds, where one atom gives an electron to another, now we're dealing with what's called a covalent bond, which is about sharing electrons. So, classic example, hydrogen. Hydrogen is H2. Well, sorry, hydrogen by itself, the element, is actually the puniest atom in the universe. It's simply a proton with an electron. That's it. No neutrons even, just a proton and an electron. It would very much like to have 2 electrons, though, and be like helium, the first of our noble gases. So if you put 2 hydrogens together, instead of one taking the electron, whatever, what they do actually is they share electrons, and you get what's called H2 gas, hydrogen gas, that has 2 electrons, each of them essentially sharing and acting as if they have 2. That's forming what's called a covalent bond. So you know the difference between a covalent bond and ionic bond. Now the problem with the way atoms share electrons is that nobody taught them how to share nicely. And so what ends up happening is that if you're a larger atom, you are able to pull those electrons more strongly than a weaker atom, a smaller atom. So it's sort of like a universe of bullies, where the bigger the atom you are, the stronger you are, the more you pull on these electrons. So in the case of oxygen and hydrogen, hydrogen, like I said, is the universal wussy. It's the smallest atom in the universe. It's literally just 1 proton and 1 electron, tiny little atom. Oxygen is a much, much bigger atom. It has a lot more protons, a lot more electrons, it's a bigger atom. As a result, it pulls on those. So in water, there's a covalent bond. The oxygen is sharing an electron with hydrogen, and it's sharing an electron with this hydrogen as well. But because hydrogen is so weak and oxygen is so strong, it's able to pull those electrons closer to itself. Now understand, it does not completely rip the electrons away from the hydrogens. They're still sharing, it's still a covalent bond, but the electrons tend to spend more time over here. Now if you remember, what's the charge of an electron? An electron has a negative charge. As a result then, the oxygen becomes a little bit negative. This symbol right here means slightly. Slightly. So the oxygen becomes slightly negative, and the hydrogen side becomes slightly positive. Now somewhere on your study guide near here, I want you to draw a bar just like this, a rectangle just like that. Then I want you to draw a line right through the middle. Let's put a plus over here, because this is the plus side with the hydrogen. Let's put a minus over here, because this is the minus side with the oxygen. What have I just drawn? I've just drawn a magnet. Make a note to yourself that water behaves like a tiny little magnet. It has this positive side, it has a negative side, and as a result, it's going to be behaving like a tiny magnet. We call this polarity. Just like my magnet, which I'll draw again here, just like my magnet has a positive and a negative pole, so does my water molecule. And so it's very polar. It's a polar molecule with a negative end and a positive end. And so it's going to behave like a magnet, meaning water molecules stick to each other. They also will stick to anything else that has a high charge to it. Think about it just for a real quick second. Remember the sodium and chlorine that we just saw? NaCl, right? The table salt? Na becomes positive and the Cl becomes negative. It's going to kind of look like a little magnet to us, right? It's got a negative and a positive side. Do water and salt interact? You betcha. If I pour salt into water, what happens? Salt crystals into water? It's like they disappear. They get dissolved. How does it happen? Well, it's because of water's strong polarity. Makes it what we call a really good solvent. It dissolves lots of things. Anything that's polar will dissolve beautifully in water. This is one of many properties that water has that we'll look at in the next lecture that make it so important for life. The interaction between water molecules is called van der Waals forces, or also known as hydrogen bonds. So if we look here, remember, if we were going to kind of label our water molecule here, the water molecule, the oxygen is slightly negative, the hydrogen is slightly positive, right? So what ends up happening is that the slightly negative side of one water molecule is attracted to the slightly positive side of another water molecule, and so forth. That allows water to stick together, gives it stuff like surface tension, makes it so that the ice is less dense than the liquid water, and so forth. Lots of really interesting kind of cool properties of water. We'll zoom into this in more detail in the next lecture. Hope that was helpful for you.